We saw the statement of spectral decomposition before. Today, we are going to cover the proof of spectral decomposition. Let me remind you what spectral decomposition was. A matrix, or I should say, a normal matrix M. We restricted ourselves to this vector space. A normal matrix can be decomposed or written as this summation. Here, important thing is that xi's form an orthonormal basis. This was the statement. This, in some sense, characterized normal matrices. We define normal matrices to be the ones which satisfy this condition. It turns out we can also say that these are exactly the matrices which can be decomposed in this form, or they have an orthonormal basis of eigenvectors. There was another interpretation which was pretty interesting, that M can be written as U star du. This is exactly the same as the equation written above. Notice that xi will be the columns of U and D is a diagonal matrix whose entries are lambdas. With these construction, you will see that these two are exact same statements. So spectral decomposition says that a matrix M is diagonal in the basis of x1, x2, xn. Remember what a diagonalizable matrices were? In the case of diagonalizable matrices, they became diagonal under some n linearly independent vectors. Now, normal matrices will become diagonal under the action of orthonormal basis of eigen. We are interested in the orthonormal basis. And the proof will construct this diagonal form one by one. The main lemma which is needed to prove spectral decomposition actually talks about the action of a normal matrix on an eigenspace. Let me first intuitively describe the main lemma, then we will prove the main lemma. Let S lambda be the lambda eigenspace of M. You remember the definition of eigenspace? It's the set of all eigenvectors which are lambda eigenvectors for M. In this case, M acts separately, I will describe this term, on the eigenspace S lambda and the perpendicular subspace to it. If you have forgotten what the perpendicular subspace is, it's the set of all vectors such that they are perpendicular to anything in S lambda. This is the complement space of S lambda. So the main lemma basically says that the action of M on the entire space is very simple. I can decompose it into two parts. It acts separately means if V is element of S lambda, implies MV is element of S lambda, and if V is element of S lambda perp, then MV is element of S lambda perp. Geometrically, if I write down my matrix with eigenvectors or basis of S lambda here and then basis of S lambda perp here, it's easy to verify that that will form the complete basis. If I write the basis like this, if I write my matrix in this basis, then M will be of this form. It will be a block diagonal matrix. It will have only entries of the diagonal. Because if I take anything inside S lambda, it will go back to S lambda. If I take anything in S lambda perp, it will go back to S lambda perp. This is the main lemma. Let's prove it. This is only true for normal matrices. We want to prove that M acts separately on S lambda and S lambda. So two parts. If V is element of S lambda, implies M is element of S lambda. Second part, if V is element of S lambda perp, implies MV is S lambda. This doesn't even require a proof. MV is equal to lambda V is element of S lambda. Any scalar multiple of V has to be in S lambda. This is trivial. Only the second part is important. Why does a normal matrix keep S lambda perp inside S lambda perp? Under its action, S lambda perp stays inside S lambda perp. Let's see why that happens. Suppose I have a vector in S lambda, the original space, and if I look at the action of star on vector V, I know, because matrix M is normal, this is where I am losing the normality of M. This is lambda M star V. Notice this shows that M star V is a lambda eigenvector. Other way to say it, M star V is element of S lambda perp. Not just M, but even M star keeps S lambda to S lambda. I did a mistake. What I want to say is that M star V is a lambda eigenvector, so it has to be in S lambda. This property easily shows property 2. How? Let's take V to be element of S lambda and W to be element of S lambda perp. Then I want to show that MW is element of S lambda perp. That means I want to show that V MW is 0. But this is same as Vm star W by the property of inner product. I should write it as M star V W. That's the correct way to write it. But this is an S lambda perp. I'm sorry. This is an S lambda. This is an S lambda perp. This is 0. This is actually true. So I have proved that if W is element of S lambda perp, then MW is also element of S lambda perp. This proves the main lemma. Remember, what did main lemma say? That M acts on S lambda and S lambda perp separately. Using this main lemma, the proof of spectral decomposition is basically by induction. How? Let me give you an idea. I will find one root of the characteristic polynomial. You remember what the characteristic polynomial of M was? Determinant of lambda n minus n. Definitely, it is an equation with degree n. It will have at least one root, say lambda. Once I know that lambda is a root, let's look at the lambda eigenspace. Call it S lambda. In this case, I know that M can be thought of as two matrices. Action of M on S lambda, which is lambda I. Correct? It just multiplies everything by lambda. And then action of M on S lambda perp. So if I write M in this basis of S lambda perp, S lambda perp, S lambda, so on, I should say again, if I write it in this basis, this will be lambda I, this will be some matrix M prime, and here I will get 0 and 0. This comes from the structure comes from my mean lemma. It says that M acts separately on S lambda and S lambda perp. So under this basis of S lambda and S lambda perp, M looks like this. It is easy to show, I will give you as an exercise, to show that M prime is also null. That means it will still have a spectral decomposition by induction, and this way I will get these different eigenspaces where each of these blocks will be diagonal. Lambda I, lambda 1I, lambda. This is showing that there exists a basis, actually an orthonormal basis, such that M is diagonal in that basis. What is that basis? It's basically the basis of S lambda, then basis of S lambda 1, basis of S lambda k. This is the whole idea of the proof of spectral decomposition. Once we know that M acts separately on S lambda and S lambda prime, then we just apply induction and things nicely fall out into a diagonal.